To build an automated physical world, engineers faced a strict challenge. How do you construct an electrical circuit that passively detects its environment without relying on a manual mechanical switch? The solution requires a highly specific type of transducer. The system needs a physical bridge capable of accepting optical inputs from the environment and instantly converting them into an electrical response. That device is the photocell. By definition, it is a mechanism built strictly to convert light energy into electrical energy. Operationally, the photocell takes a highly unpredictable environmental variable, ambient photons, and translates it into a precise proportional flow of electrons. This simple energy conversion, turning light into an electric current, forms the hidden bedrock of modern civic automation and security systems. To understand how this works in real-world automation, we have to look at the internal architecture of the sensor itself. This hand-drawn schematic defines the baseline structure of the photocell circuit. We start with the external power circuit. A continuous direct current is supplied by a battery source, establishing polarity. Placed in line is a microammeter, essential for tracking minute fractional flows of electrical current. The actual sensory environment is contained within an evacuated glass tube, housing two separated metallic elements. The first is the cathode. Wired to the negative terminal, this curved plate acts as an electron emitter. Facing it is the anode. This smaller rod acts as the collector, wired straight to the positive terminal. Crucially, there is physical, empty space isolating the cathode from the anode. Because of this vacuum gap, the circuit is physically open. Without an external trigger, the electrical current stays at zero, leaving the entire system inert. To change the circuit state from inert to fully active, the system requires a powerful external trigger, incident light. Photons physically enter the vacuum tube and strike the specialized, highly photosensitive surface of the curved cathode plate. At the atomic level, this triggers an immediate energy transfer. Incoming light is absorbed by electrons in the cathode and instantly converted into kinetic energy. This energy transfer causes the violent ejection of electrons directly from the cathode surface. Because they carry a negative charge, they are repelled by the cathode and pulled forcefully across the vacuum toward the positively charged anode rod. The macro effect on the system is immediate. This constant stream of jumping electrons successfully bridges the physical gap, effectively closing the open circuit. At the measuring station, the microammeter immediately registers a continuous, positive electrical current flowing through the loop. The device has successfully translated ambient light into a measurable electrical language, allowing the physical environment to act as a live trigger for the circuit. This handwritten list details 5 practical applications for a photocell. By analyzing it, we can see exactly how engineers utilize this newly generated microampere current in real-world systems. The first operational mode is intensity measurement. This approach treats the electrical output as continuous analog data. Because the volume of ejected electrons scales perfectly with the brightness of the light, the current provides a fluctuating metric of ambient intensity. Item 1, light meters and cameras, uses this analog data to calculate perfect exposure. The second operational mode relies on a completely different logic, beam interruption. This utilizes strict binary or threshold logic. In this setup, a steady beam of light aimed at the photocell creates a high, constant baseline current. When a physical object blocks the light path, the electron stream abruptly stops and the current instantly plummets to zero. This sudden drop threshold logic drives the second application, automated street lights. The moment ambient daylight falls below a specific voltage threshold, the drop in current forces the external circuit to switch the lights on. We see the same invisible tripwire logic in bank vaults. A light beam broken by an intruder drops the current, instantly triggering a theft warning. For the fourth application, the circuit logs rapid beam interruptions. This allows a system to incrementally count the exact number of persons entering a hall. Finally, civic enforcement uses this logic to detect traffic law defaulters, measuring the precise time between broken optical beams on a roadway. The engineering utility of the photocell relies on this dual nature. It serves as both an ultra-precise measuring gauge and an instant Boolean switch, dictated entirely by how the external circuit is programmed. Reviewing the complete architecture reveals how it bridges the optical and electrical worlds. Incident photons strike a cathode, forcefully closing a vacuum circuit with ejected electrons. This reliable microampere current acts as the steady heartbeat for complex logic systems. Every one of these distinct applications, whether perfectly exposing a photograph or instantly triggering a bank alarm, relies entirely on this exact same atomic-level event. The device achieves perfect environmental awareness with zero moving parts, relying purely on the physics of electron manipulation. Ultimately, the photocell serves as the ideal translator for automation, cleanly reducing chaotic physical variables, like shifting sunlight and human movement, into the precise, manageable language of electrical current.